Okay, thank you, Jana, and thanks to the rest of the organizers for putting up this really nice workshop and for inviting me to give a talk. So today I would like to talk about this work that was done in a great collaboration with Javier Magan, who's at the Instituto Balseiro in Bariloche, and with Brian Swingle, who's at Brandeis. And what I'm going to tell you is based on these two papers that appeared over the last year. Okay, so let's start with the motivation. Exploring the black hole Hilbert space is a really important open problem in holography. And in particular, one question we can ask is, what do the typical black hole microstates look like? Okay? So there's different ways to try to approach this question. A constructive way is to start from the thermofield double, which is holographically well understood. Its semiclassical dual is the Einstein-Rosen bridge of an eternal black hole in ADS. So start with this state and apply operations on it in order to reach more generic states. Okay. The observation over the past decade or so of work is that more complex microstates of the two black holes, which are equilibrated, they contain longer Einstein-Rosen bridges in the black hole interior. So this is a particular example of operation, which is the time evolution with the decoupled Hamiltonian. This will generate some time-evolved thermofield double state, which will eventually equilibrate in a system of finite entropy. And what is believed is that the wormhole dual to this state is longer than the wormhole for the thermofield double. Okay? However, complexity is a difficult quantity to pin down precisely in holography. And moreover, something that I want to emphasize during my talk is that complexity doesn't necessarily mean genericity. Okay? So in particular, I would like to have a more systematic way to try to approach typical states of black holes. So in order to emphasize this second point, let me just first define what I mean by typical. So let's just consider a situation of an infinite temperature situation in a finite entropy system. Here, typical for a two-sided Hilbert space, it just means Haar random. So essentially, the two-sided state dual to a Haar random unitary, that's what I'm gonna be calling typical in this infinite temperature situation. Another way to call this state is a random maximally entangled state between the two systems. Okay? So what I was saying before is that if we start from the thermofield double within the infinite temperature setting would correspond to the choice state of the identity operator, and we just apply some time-independent Hamiltonian to it in order to reach some other states in Hilbert space. These states that we would reach, which have the form of the choice state of e to the minus ith for a time-independent Hamiltonian, would generally be very different from a Haar random state. Okay? There's many ways to see this. One way is to look at the spectrum of a Haar random unitary. So the spectrum of a Haar random unitary consists of some phases which are statistically correlated with each other to repel each other. Particularly here I'm showing the nearby eigenphase repulsion characteristic of the distribution of eigenphases of a Haar random unitary. So as you see, the distribution is a Wigner-like distribution, and in particular, nearby eigenphases are statistically uncorrelated to repel each other. This class of correlation is very hard to obtain by just time-independent Hamiltonian evolution, even if the Hamiltonian is completely structureless. And even if time here is very, very long, so exponential in the entropy. Okay? So this already shows that very complex states, so e to the minus ith for very long t, would be distinguishable in a sort of microscopic sense from typical states of the black hole. So in order to apply these considerations to black holes, we need to define a finite temperature version of what typical means. So here I will just take my Haar random unitary and sandwich it in between two factors of the square root of some equilibrium density matrix, which for all purposes you can take as the canonical Gibbs state at some temperature. So the choice state of this operator is what I will be calling typical at finite temperature. Okay. So in this talk, I will construct states of two black holes with long wormholes and with a large number of matter inhomogeneity supporting these wormholes. So I will refer to these wormholes as caterpillars for obvious reasons. And the goal of the talk will be to show that the ensemble of caterpillars forms a quantitatively generic ensemble of microstates of the black hole. In particular, the take-home message of my talk is that the ensemble of caterpillars of average length t forms a t-random ensemble of microstates of the two black holes. So the goal of my talk will be to derive this kind of relation and to also specify what I mean by t-random over here. Okay, so in order to explore the black hole Hilbert space, we will use time-dependent Hamiltonian evolution instead. And so everything that I'm going to say from now on will be specific to SYK, so I will just focus on SYK. But in principle, what I'm going to say could be also generalized to higher dimensional holography. Okay. So let's focus on SYK. I'm going to define a Brownian Hamiltonian as some time-dependent Hamiltonian of the following form. I'm going to take some operators. Here, I'm just specifying length q Majorana strings, and I'm attaching time-dependent couplings to these operators. So a Brownian Hamiltonian is defined by an ensemble of white noise correlated random couplings. Essentially, that means that the couplings, they are uncorrelated from each other at different times. Okay? And moreover, I will take these couplings to be Gaussian random. So this is essentially the variance of a white noise correlated coupling, and this ultra-local term in time represents the fact that the couplings at different times, or in other words, the Hamiltonian at different times, is uncorrelated with each other. Okay? So this dynamics is the continuous time version of what is known in the quantum information literature as a random quantum circuit. Here I'm representing a random quantum circuit which corresponds to a quantum circuit where each layer of gates is chosen randomly from some distribution of gates. So the difference between the two dynamics is that the Hamiltonian I defined above is all-to-all in the sense that it couples all of the degrees of freedom together at each layer, whereas this one is local. But the late time physics of both situations should be pretty similar. And heuristically, this class of Hamiltonian will generate, if we apply it to the thermal field double, it will generate some Brownian motion in Hilbert space, and this will, in principle, eventually let us explore Hilbert space densely and reach typical states. Okay. So another reason to believe that this is true for this class of Hamiltonians is that for random quantum circuits, this is known. So random quantum circuits are known to eventually generate approximate high random unitaries. Okay, so in order to apply these considerations to black holes, we need to define a finite temperature version of this random quantum circuit. So in order to do that, what we did in our paper was to apply layers of time evolution with the random circuit, and then cool the system down with some Euclidean evolution and some bare Hamiltonian over here. So the bare Hamiltonian, you can think of it as the SYK Hamiltonian, which takes the state of the system, if we input it over here, and cools it down. Okay. So this operator, W of t, represents a finite temperature version of a random quantum circuit. And in particular, what we did with this operator is to define two-sided states by sandwiching this operator in between two Euclidean evolutions by beta over 4 and considering the choice state, the two-sided state associated to this operator. So this might seem a little bit ad hoc for you at the moment, but let me show or represent what the situation should look like with a toy model. So let's just consider that this operator is very low temperature, so it should be describable by JT gravity with matter. And let's go back to the model of the random circuit where we just take discrete time steps and insert some operator at each layer of the circuit. So here I'm replacing, in this toy model, I'm replacing the Brownian time evolution with the choice of some operator or some matter operator with some property. So you can think of these different matter operators as having different flavors or as having different conformal dimensions. So this Euclidean preparation on the prepares a state on the two-sided SYK on two copies of the SYK Hilbert space, which looks like this, and this kind of state is known to semiclassically be dual to a two-sided black hole with a large number of matter insertions in the black hole interior. So this very heuristic sort of toy model of what's going on in the real finite temperature Brownian quantum circuit already tells us about the geometry of the black hole interior. At least it gives us some idea of what it might look like. So we will be interested in computing the length of the wormhole average over the ensemble of caterpillars. Recall that this is a single realization of the random circuit. We could have chosen some other colors. This would correspond to some other state within our ensemble of states. And we are interested in the average geometric length of the wormhole within this ensemble of microstates. From the toy model, it is natural to expect that the average length of the wormhole grows linearly with the total circuit time, with the total number of matter insertions. And moreover, another property which we expect from the toy model is that if we take different instances, say with operators with different conformal dimensions, the geometric lengths in between them might change slightly, but the average geometric length of the wormhole should well approximate the actual length for single instances. So what I'm saying is that the length of the wormhole should be self-averaging over the ensemble of states if the number of insertions is large enough. Essentially, this happens from a central limit theorem kind of argument, where the length of the wormhole is statistically distributed as a Gaussian random variable with some average value and with some variance which is suppressed by the number of insertions. Okay, this is just the heuristic picture. What we did in our paper was to actually try to derive it for the ensemble of finite temperature random circuits. So the way to do that, what we did was to consider the norm of a state in this way, and we computed the average norm over the ensemble of caterpillars. So essentially, we took this quantity, which is the boundary partition function on a closed contour. So the lower half prepares the bra, the upper half prepares the ket. We took the average over the Brownian couplings of this quantity. So what happens is that the average over the Brownian couplings of this quantity generates effective interactions between the bottom and top contours in terms of a time-independent effective Hamiltonian. Okay? So the average norm can be rewritten as the survival amplitude of the thermofield double by some Euclidean evolution with some time-independent effective Hamiltonian. This is essentially the horizontal way to read this amplitude, where we input the thermofield double over here, thermofield double over here, and we evolve the full two-sided state with some time-independent effective Hamiltonian. So the effective Hamiltonian has this form. It's just the SYK Hamiltonian on the bottom replica, the SYK Hamiltonian on the top replica, and then there's this bilocal fermion interaction coming from the average over the Brownian couplings. So this class of Hamiltonians were extensively studied by Maldacena and Chi in the large N limit, and we can use their technology to actually find what the semi-classical disk solution is to the average norm, computing the average norm over the ensemble. So in particular, in the bulk theory, so we are now trying to evaluate this average norm, this quantity in the bulk theory. This is evaluated via a bound solution of the geodesic length between the two replicas. So this is essentially the low energy effective action that Ahmed described in his talk very nicely. And so I won't go into much details, just to mention that because of the fermion interaction, there's this additional term in the potential, and this makes the potential contain bound states, as Ahmed was describing. Okay? So what happens is that the solution for this particle, this particle bounces, it starts at -infinity, it reaches some maximum value of the length, and it goes to -infinity again. But because of this potential, the value of L for very large t is mostly constant through the contour. And what this essentially generates is an approximate translation symmetry of the disk solution, so that the disk gets stretched and it looks more like an interval capped off smoothly by two pieces over here. So we are interested in the length of the wormhole. The length of the wormhole should be contained within the geometric length of this slice, okay, which is the natural analytic continuation to prepare semiclassical states. And so because of this Euclidean time translation symmetry of this trajectory, this Euclidean time translation symmetry essentially translates into the spatial isometry of the Einstein-Rosen bridge, okay? So what I'm saying is that on average over the ensemble of states for very large values of t, the geometry looks like a cylinder which has an approximate isometry, spatial isometry in the black hole interior. And this solution is representing that. So this argument already tells us that the total length of the wormhole, the average length of the wormhole, should grow linearly with the preparation time of the random circuit. However, in order to pin down the exact growth, we can find out all of the details about this previous solution and write down a formula for the average length of the wormhole as a function of the boundary time. So we find the following relation. So on the left-hand side, I'm representing the length of the wormhole in units of what I will be calling the matter correlation scale L delta. So the matter correlation scale, you can define it as the largest scale of matter correlations on the wormhole. It can be defined from the decay of a spatial two-point function on the wormhole for the lightest excitations of this Malathena-Chi Hamiltonian. On the right-hand side, there's the boundary time t, and then this t is measured in units of the inverse gap of the Malathena-Chi Hamiltonian, which can be fully computed in these models. Now, additionally, there is some onset time of this linear growth of the length of the wormhole, which has to do with the fact that there will be excited states propagating through this geometry. And so for this argument to work, all of them have to decay. And so in the Malathena-Chi Hamiltonian, there's order n, there's actually n fundamental excitations on top of the ground state. And this produces an onset time of the linear growth, which is of the order of the scrambling time if the gap scale is of order 1. Okay? So this relation essentially shows that the bulk geometry, the average geometry of the bulk wormhole, behaves as some sort of random circuit where the length of the wormhole parameterizes the total time of the circuit. Good, so that is the geometric part of the talk. The goal is now to relate this linear growth of the length of the wormhole to some microscopic measure that characterizes the ensemble of microstates that we constructed. So in order to explain what this notion is, let's just go back to the infinite temperature situation, so no gravity for the time being. The question we want to ask is how distinguishable is our ensemble of states, U of t, from the ensemble of typical states, U har, okay? So in order to quantify this, we consider what is known as the kth frame potential of the ensemble of states. So the frame potential is defined as follows. Essentially, you take two independent instances of your ensemble, you take their mutual overlaps to the 2kth power, and then you average over the disorder that defines the ensemble, in this case, the Brownian couplings. So this kth frame potential is some statistical moment of the ensemble of states. It's just a number. For the Haar ensemble, for the ensemble of random states, the value of this frame potential is k factorial for k smaller than the dimension. And this can be derived using techniques in Haar integration. Okay. So essentially, we will be interested in comparing these two numbers. The reason is that the difference in frame potential controls the quantum information distance, the two-norm distance, between the moments of these two ensembles. So if fk of t is k factorial, that means that our ensemble of states is statistically indistinguishable from the random state ensemble up to the first k moments. Okay? So that has a name in quantum information. It's called a quantum state k design. In these infinite temperature situations, since I'm just talking about choice states of unitaries, we could have also said that the ensemble of unitaries U of t forms a unitary K design. Now, these frame potentials have a physical interpretation in terms of some average notion of a 2K point out of time order correlator, as was emphasized in this paper. And the idea is, for instance, that if we have a unitary 2 design in front of us, that means that typical member of a 2 design will be scrambling with respect to the conventional 4-point out of time order correlator. Okay? So this K design is a 2K generalization, a measure of a 2K version of the out of time order correlator. Good. So frame potentials are interesting in gravity for 2 reasons. First of all, they characterize the microscopic randomness of the ensemble of states. But moreover, they are disordered 2K replica partition functions, which can be evaluated in the larger limit gravitationally using the gravitational path integral. So here I'm representing the second frame potential. This just corresponds to the 4th moment of the overlap between 2 independent instances. So each boundary computes some overlap between 2 states. There's an average over the disorder that defines these states, which correlates the different replicas. And in principle, in larger systems, we expect that this quantity can be evaluated in a larger limit, semiclassically. So in order to show how this works actually for SYK, let me just comment that for our states, so for the Brownian time evolution, the average over the Brownian couplings in the different replicas will generate effective interactions. And one can show that the K frame potential in our case, it just corresponds to an thermal partition function of an effective Hamiltonian HK, which couples the 2K replicas together. And the time, so the circuit time that parameterizes the states, just plays the role of the inverse temperature in this thermal partition function. So for K equals 1, the effective Hamiltonian is just the infinite temperature version of the Maldacena-Chi Hamiltonian I was writing before. And one can, in fact, diagonalize this Hamiltonian exactly for finite n and solve what the first frame potential is for the ensemble of infinite temperature versions of the states that I was discussing in this talk. Okay? But what is more interesting for us is that this frame potential can be evaluated, F1 can be evaluated in the larger limit using the G and sigma variables of SYK and doing a saddle point approximation within these variables. So in particular, what will be relevant for us is the late time value of this first frame potential, which corresponds to the contribution to this thermal partition function coming from the ground states and first excitations of this effective Hamiltonian. So it turns out that this contribution is captured in the larger limit by a saddle point of the G and sigma variables, which has inter-replica connectivity, and in this sense is a wormhole. And in fact, this wormhole is the same as the plateau wormhole of the Brownian spectral form factor, because essentially at infinite temperature, F1 of t is a Brownian, it's a time-dependent version of the spectral form factor. This wormhole was written in this paper by Sasieta and Stanford. Okay, so this wormhole produces this value for the frame potential at late times. So let me now explain what this value is. So first of all, at infinite times, the frame potential asymptotes to the number of ground states of the effective Hamiltonian. So that's where this factor of 2 comes from. Essentially, there's 2 different ground states, 2 independent ground states of this effective Hamiltonian, which correspond to the 2 infinite temperature thermal field doubles between these 2 replicas. So there's 2 essentially because this system is fermionic and there's a global symmetry, which is fermion parity. So these 2 correspond to the different fermion parity thermal field doubles between the 2 replicas. In systems without symmetries, we would expect a factor of 1 over here, just 1 ground state. Now, on top of the ground state, the first excited states contribute with this term. Essentially, their contribution is exponential, which is natural from this point of view, and this can be obtained from this wormhole. And additionally, this factor of n counts the number of first excitations, which is n, because the first excitations just correspond to single fermions on top of each ground state. Okay, so this form of the latent value of the first frame potential is obtained by this wormhole in a larger limit. Good. So for k greater than 1, the effective Hamiltonian is a 2k replica version of the previous effective Hamiltonian, which is more complicated. In particular, the effective Hamiltonian contains anti-ferromagnetic type of interactions between certain classes of replicas and ferromagnetic interactions between certain others. That means that the fermion bilinears will come with a plus sign or a minus sign, essentially. So what happens is that the ground space of this effective Hamiltonian, which controls the latent value of the kth frame potential, this ground space will break replica symmetry into k copies of the 2 replica ground space. And what this means at the level of the large n saddle points contributing to the frame potential is that the ground space contribution, the latent contribution, will just correspond to k factors of a 2 replica wormhole joining forward and backward replicas. Okay? So for k equals 2, there's actually 2 different ground states, 2 different topologically distinct ground states associated to the different permutations, which are the ways to connect the forward and backward replicas in different ways. Okay? So for general k, the ground states are labeled by elements of the permutation group of k elements. Moreover, in the larger limit, the first excited states are additive, and so the first excitations just correspond to single fermions on top of each 2 replica ground state. So what this produces for the frame potential is the following form. At infinite times, the frame potential just counts the number of ground states, which is k factorial. This comes from the number of ways to connect forward and backward replicas with 2 replica wormholes. And then there's a factor of 2 to the k coming from the fact that each 2 replica wormhole can come with a plus or minus fermion parity. So on top of that, there's the contribution from the first excited states, which decays exponentially in time. And it counts with the energy scale is the gap of the 2 replica effective Hamiltonian, essentially because of this fact that the excitations are additive. And the number of first excitations is just n coming from the number of fermions you can excite on each replica, and then k coming from the number of 2 replica wormholes per ground state. Okay, so one can ask now, like we can take this form of the kth frame potential at late times, and we can ask how long does it take for the frame potential to approximately become close to k factorial. Now I will not talk about this additional factor, but you can ask me later if you're interested. So this form of the frame potential produces a linear growth in the sign. That means that the time that it takes for fk of t to become close to k factorial is linear in k. So the amount of randomness of our ensemble of states grows linearly in time with a slope which is given by the gap scale of the 2 replica effective Hamiltonian. Okay? There is also some onset time of this linear growth owing to the fact that there's higher excitations on these wormholes that have to decay. And then there is some other time scale associated to the degree of approximation that we're making by approximating fk of t by k factorial. So fk of t actually never becomes k factorial, only at infinite times. This t epsilon is just the degree of approximation in our definition of approximate quantum state k design. So in the case of finite temperature, the situation is very similar. The difference is essentially that we need to compare our ensemble of states to the ensemble of equilibrium random states. And the story is essentially the same. The kth frame potential of our ensemble, it can be rewritten as a replica partition function of some effective Hamiltonian, which is the finite temperature version of the previous effective Hamiltonian. And so for the 2 replica quantities, so the first frame potential, this quantity is a version of the Maldacena-Chi thermal partition function. It's just some thermal partition function of this effective Hamiltonian. So at very late times, the sort of fundamental saddle that we're interested in is the 2 replica wormhole, which dominates this thermal partition function at very late times, or low effective temperatures. So this saddle is known is just the double trumpet geometry, where the bottleneck modulus has been stabilized by the Malasenachi interaction. Okay, so essentially we can build our 2K replica ground states and everything and compute the frame potential from the properties of these two replica wormholes. What we get is the similar expansion at late times, and this produces a linear growth very similar to the one before. The main difference is that the gap scale is now the gap of this effective Hamiltonian, which is the finite temperature version of the one before. So you see that both randomness of the ensemble of states and the length of the wormhole grows linearly with the circuit time with the same slope. And so both linear growths can be combined into the following statement, which is the main result of our work. The ensemble of caterpillars of average length L and matter correlation scale L delta forms an approximate quantum state K design of the black holes for a K which is proportional to L over L delta. On the left-hand side of this equation, K represents a microscopic measure of randomness of the ensemble of states. On the right-hand side of this equation, L over L delta represents a geometric property of the emergent black hole interior. Okay, so this is our main result, but let me end with some future directions and some comments. So it would definitely be nice to have a more detailed characterization of individual instances of our ensemble of states. That's very hard. You need to solve some very hard problem in the bulk, but in principle, it could be done. Then it would be nice to have the explicit constructions of caterpillars in higher dimensional ADS-CFT with Brownian sources for bulk fields. And yeah, let me end with two comments or two interesting questions that I would like to know the answer of. First one is whether caterpillar states have firewalls or not, where firewall is understood as a high energy shock very close to the horizon as measured by the infaller. Okay? An observation is that frame potentials are invariant under global unitary multiplication of the ensemble of states. So this means that they are invariant under external boosts. So future evolved caterpillars, which probably do not have this class of firewalls because all of the matter would have already fallen into the black hole interior, they have the same frame potentials as the past evolved caterpillars, which probably do have firewalls because the matter in the interior is highly boosted with respect to the external observer. So this means that at least in principle, we can provide ensembles of states which have firewalls and other ensembles of states which do not have firewalls, which are K-copy statistically indistinguishable from each other. And let me end with some more speculative regime, which is exponential values of K. So in my talk, I've restricted to polynomial values of K because there we hope to have some control, so some semi-classical control of the frame potentials. But in principle, we could just extrapolate to exponential values of K. And in this case, caterpillar states are supposed to cover Hilbert space densely. So this means that the ensembles of states that I built, they are supposed to form a uniform covering of Hilbert space up to some resolution. And in particular, this means that for any state of the two black holes that you can think of, there should be a caterpillar within some epsilon distance in Hilbert space from it. And what the physical implications are of this statement are I think they are very unclear, but it would be nice to know this better. So with this, I would like to thank you all for your attention.
The finite temperature case, what could the ensemble converge to the equilibrium ensemble you define, like instead of the genuine carbon?
So, okay, yeah, that is a subtlety that I didn't mention too much about. Essentially, the point is that when you do these average overcouplings, there's this effective Hamiltonian that shows up, which is the Malasenachi Hamiltonian. And so for very large values of t, the only transverse state which propagates over here is the ground state of the Malasenachi Hamiltonian. And essentially, it boils down to the fact that the ground state of the Malus energy Hamiltonian is similar to a finite temperature thermofield level. But yeah, I could show you like how to derive this more explicitly, but that's essentially the main property we use.
Questions? Yes.
Have you thought of any sort of generalizations of this, perhaps with tensor networks, if there is a way to rewrite it by a temperature ensemble?
Yes, so the tensor network model of this, the caterpillar should be a random circuit in the interior, which could be all-to-all, and then some isometries representing the external regions. I think that should be the model. And maybe, yeah, it would be nice to study properties of those tensor networks. So they would be like a finite temperature versions of a random quantum circuit in that the IR degrees of freedom, they form a random quantum circuit, but then they are embedded into the UV by some holographic isometries.
Or how you want to choose those isometries and perhaps, like, I guess the obvious choice is that you optimize that to CFD perhaps, that
You could, in principle, choose two Mera tensor networks and plug them here. This would be like the horizon of the black hole. Yeah.
So when I think about Brownian couplings, then when you average, when you take different replicas, then like you identify the different, the same location in different replica.
Right, exactly. That what generates local interactions in time between different replicas.
But if I think about this Berkeley system, where I don't have an obvious way of identifying different replicas, is that a problem?
Sorry, can you repeat that?
If I take multiple replicas, then is there always a unique way to identify the points?
No, actually, like for a large number of replicas, the effective Hamiltonian looks like this. It couples all of the replicas together in pairs. So the fact that the coupling is bilinear between different, like it just involves a fermion on one replica, fermion string on some other replica, comes from the fact that the couplings are Gaussian.
Between the same points, right? It's
Here you have k replicas forward and k backwards, and all like because you're squaring the full thing, you will get like all possible contributions between all of the replicas.
all copies are the same kind, right?
Yeah.
You mentioned that this distribution was invariant under boosts, but it seemed to me that maybe you didn't say that.
No, I so the Haar ensemble is invariant under boost. This one isn't. What you generate is a new ensemble which has the same randomness properties as the previous one. So in the tensor network model, it's like just plugging some fixed unitary over here. And this does nothing for the frame potential. So the ensemble would have the same statistical moments, at least as far as the frame potentials are concerned. And so you could just time evolve forwards over here or time evolve backwards. You would generate two separate ensembles. They would be statistically k-copy indistinguishable from each other.
Any last questions? All right, let's thank Martin again.